This is ME5356 Smart Material Presentation for question 36 of Exam 2. My name is Ian Stratton and we're going to discuss the use of self-sensing nanoparticle concrete in structural applications. It can be seen that concrete is one of the world's most useful resources. Much of the infrastructure that surrounds us is constructed from it. Compared to other construction materials, concrete can resist corrosion and fire while combining high compressive strength with relatively simple construction technology. And its simplest form is just water, aggregate, and cement. So if we take a look at the problem statement, it says that concrete structures do not always behave as intended, and if not monitored and maintained, can result in catastrophic failure. In 2014, 4 million metric tons were produced, and so the potential impact that a smart material could have is massive. The graphic here was taken from a civil engineering website. Just shows the flowchart for inspection and evaluation process and also the typical life cycle of the material. The capabilities that a smart material can provide in this application are to provide what's being called health monitoring, and also improvements to the mechanical properties. By introducing smart capabilities into the concrete material, we're able to monitor some critical parameters without having to perform destructive testing. A few examples are listed on the slide where things like stresses, moisture content, chloride content, and presence of cracks can be monitored. And additionally, the nanoparticles also increase the mechanical properties of the material, where some of the traditionally limiting characteristics can be improved. If we first consider the existing methods for monitoring the health of concrete, we see that there's a list of tests available that can be costly to perform on large scales. There's a few examples here from the Atomic Energy Agency in Austria. There's some ultrasonics, some visual, some infrared methods, etc. As you can imagine, the advantage of a smart material can be very useful when carrying out large works in concrete, such as in dams or bridges, where the volume of concrete involved is quite massive. If we can automatically or remotely monitor data on the condition of the structure, then we're going to see improvements in safety, reliability, and durability, etc. Further, the improvements in mechanical properties can be seen through the use of smart materials where resistance to crack formation is advantageous. Also, the resistance to crack formation during the curing process can be controlled. If the values of humidity and temperature are known, the premature drying of the concrete can be avoided by hydrating it using the nanoparticles. So if we look at the material types, we can see that there's the bulk or the matrix material, and then there's the functional fillers. And these can either be macro, micro, or nanoscale, or hybrids. We'll be focusing on the nano. Some materials that people have experimented with are presented in a table, together with some of the properties or the benefits that they provide. Nanoparticles in powder form, such as nanoiron, have been widely utilized in cement and concrete. We can also see that hybrids exist where a combination of materials forms are used. Here the fibers are mixed with nanotubes to improve the sensitivity and also the sensing reliability. And NGP at the bottom here are carbon-based conductive nanoparticles made from graphite. The principles of operation for the sensing characteristics stem from the change of the conductive network inside the material. So by measuring the volume of the electrical resistance or conductivity, we're able to characterize its sensing behavior. It can be seen that there's a variety of electrode materials to consider, as well as how to affix these and the arrangement or layout for them. This figure here shows 6 commonly used systems from a review paper, and there was a 4-probe method that was found to be the most recommended using a DC power supply, but also a 2-probe method, equally usable. Some other problems were presented with respect to fixing the electrodes on some material where some preferred to embed it, while others wanted to adhere it. And ultimately, however, the data is recorded using an instrument and then it can be analyzed. So regarding the mechanical properties, the major principle that nanoparticles introduce is the control of the hydration rate. Since the spacing between the individual particles is so tiny, they are distributed at a finer scale as compared to, for example, traditional fibers. In the past, cement powder was deemed to be the finest component of binding aggregates to form conventional concrete. And if we look at the figure, we can see that the particle size is greater and surface area is much less than that of the engineered concrete. So with the advancement of nanotechnology, better performance is anticipated by reinforcing the cement matrix at the nanoscale and taking advantage of the increased surface area to control cracks. Here's a look at the performance characteristics under monotonic loading for self-sensing concrete. The plots are of the change in resistivity over baseline resistivity and show both the tensile and compressive behaviors. So for the load and tension, we can see that it rises steadily as the particles are pulled apart, further apart from each other. However, for the compressive load, there's an initial state where crack compaction occurs, and then there's a steady state where crack germination occurs, and then there's a rise as the increase in resistivity due to new cracks extending. When we look at the cyclical loading, the performance characteristics for compression and tension tend to be similar though. When the stress is below 30% of the ultimate tensile strength, both the baseline resistivity and change in resistivity are both reversible. As the stress increases, we can see how the baseline becomes irreversible. And then once above 75% of the ultimate tensile strength, both of them are irreversible. It can also be seen that many other factors can affect resistivity and thus can be sensed. The concentration of the filler, for example, using the matrix, the shape of the filler, the water content, the type of environment. And the types of mechanical performance characteristics can be seen in this table, and this is taken from a review paper for nanocarbon engineered multifunctional composites. And it can be seen that the introduction of carbon nanotubes provides very large improvements in, for example, the tensile strength and the hardness, I think, increased by 600%. Fracture toughness and ductility also saw improvements by over 100%. So what can all of this do for us in terms of current and potential applications? If we consider the application of structural health monitoring, then much of the civil infrastructure that surrounds us could be a candidate. We've all seen footage of collapsed bridges and highways on the news, and this type of event can probably be prevented with sensing concrete. On a larger and potentially more devastating scale, installations such as dams and nuclear power plants could be ideal candidates, seeing how they are the structures that depend heavily upon the integrity of concrete to ensure safe operation. Other applications could be seen in traffic detection, where sensing concrete could monitor vehicle movements and allow for traffic management to improve safety and efficiency, or even be used at borders to improve the security. So to summarize what we've looked at, we saw how concrete is an inexpensive and versatile material and used in huge quantities, but it's limited by its degradation over time. The nanoparticles have been shown to greatly improve the mechanical properties of the material, making it even more versatile and desirable in structural applications. We've also seen how nanoparticles can introduce self-sensing capabilities into the material. So these can be an intrinsic part of the material and not require costly additional apparatus to perform tests or inspections, thereby providing for remote monitoring of structures. And finally, nanoparticles can also improve the workability of the material, making it flow better, and so then it can be tailored for particular applications. Overall, however, it can be seen that the potential application is quite huge. In this paper from 2015, the authors set about to develop a material that had improved flexural strength and self-sensing capabilities. What they did was to add carbon nanofibers to fiber-reinforced composites using a superplasticizer and some ultrasonics, and they created a material that could perform well in moist and sodium chloride environments, such as those found at power stations. So the results indicated that the material can provide an effective and safe way to monitor the concrete under different loading and also under exposure to different conditions. Most interesting, though, is that the material can be used as a sort of stress sensing skin, which enables it to be applied to existing structures as well as new ones. These were the references that were used in the presentation, and this is the end of the presentation. Thank you for your attention.